All right, welcome everyone. Look, it's that time. Let's dive right in this explainer and get you ready to absolutely crush your control system's final. Today we're going to bridge that famously frustrating gap between pristine textbook theory and the totally messy physical reality of engineering. So if you've been struggling to connect the math on the whiteboard to the actual pipes and valves in the lab, well, you are in exactly the right place. Let's do this.
Because let's be real, this exam, it is not just about memorizing a bunch of equations. It's the ultimate test of your engineering intuition. The real question you have to ask yourself is, can you survive the collision of perfect math and completely unpredictable physics? That's what separates the novices from the true engineers. And honestly, that's exactly what we're going to master today.
Okay, so take a look at this. It basically represents our entire syllabus packed into one single concept. We start at the top with our idealized theory, our reference inputs. Then we pass through the controller, computing all those nice, clean error signals. But then we hit the plant, the physical system. And by the time we get to the actual output reality at the bottom, things look very different. Our entire job as engineers is to navigate that exact gap.
So here is our game plan for today's exam review. We're hitting core concepts and set points, the ideal design blueprint, the messy physical reality, hardware execution failures, the multivariable trap, and finally, mastering complex system control.
All right, Section 1, core concepts and set points. Let's make sure we understand the core mission.
Starting with the absolute basics, the stuff that should already be on your flashcards. Before we can even think about designing complex algorithms, we have to ask, what is a control system actually trying to achieve? Everything, and I mean literally everything in this course, centers on the set point. This is your precise, ideal target value. It's the destination. In any physical process, whether you're regulating the temperature of a chemical reactor or managing the altitude of a drone, you have a target that you must fiercely defend against constant disturbances, or maybe smoothly adjust over time.
See that dotted line representing the output? That's our set point. Now, deviations from it happen for two main reasons. On the left side of the timeline, you can see the system gets suddenly thrown off course by external disturbances, just unwanted environmental inputs pushing us away from our goal. Then, a bit later on, the dotted line itself jumps up. That's an operator adjustment. It's an intentional change to the target by a human or a central system. A good controller has to handle both of those scenarios seamlessly. Now, because of those two specific scenarios, you absolutely have to know the difference between regulatory control and servo control for the exam. Regulatory control is all about disturbance rejection. It fights to neutralize disruptions and stabilize the whole system. Servo control, on the other hand, is about target tracking. Its entire job is to rapidly and accurately follow a target that is constantly moving.
When we look at these two paradigms side by side, their goals are literally night and day. On the left, regulatory control is just holding the line. A disturbance hits, the output spikes, and the system fights tooth and nail to stay still and get back to that fixed set point. But over on the right, servo control is all about agility. The set point moves and the system immediately races to catch up and lock on to the new target. It's stabilization versus agility. Burn this concept into your brain for test A.
Moving right along to Section 2, the ideal design blueprint. This is basically your four-step cheat sheet.
Listen, if you only remember one single process for designing a controller from scratch on this exam, make it this four-step blueprint. Every successful design follows this exact sequence. First, we audit our objectives and our capability thresholds. Second, we map our critical variables, asking ourselves, what are we manipulating and what are we measuring? Third, we architect the control structure based on the specific problem. And fourth, we execute the actual mathematical algorithm.
And check out how it all connects. You've got feedback loops, pulling data from the output straight back to the beginning to correct errors. But look right below that. Feed-forward loops use past and present system data to literally predict and dictate future control inputs before an error even has a chance to happen. It's a completely integrated ecosystem.
Okay, Section 3, the messy physical reality, or as I like to call it, where the textbooks lie to you.
Seriously, grab a red pen or highlighter right now. This is exactly where students hemorrhage points on the final. We need to talk about applying simplistic textbook assumptions to real life. Do not be fooled. What you see on the left is your homework. Clean, isolated boxes, straight lines, perfect linear models. The right side, that's what the lab actually looks like. All those theoretical clean boxes immediately shatter when they hit the chaotic, intertwined reality of bent pipes, leaky valves, and mechanical wear and tear. You have to anticipate this chaos in your math.
To actually survive that transition from math to metal, you've got to master this 2x2 matrix, the 4 pillars of real-world complexity. You need to sort your system's flaws by what's mathematical versus what's physical, and by what's predictable versus what is totally unpredictable. If you can categorize a system's flaws into these 4 distinct buckets, you can figure out how to compensate for almost anything. Because here's the hard truth. Your controller is really only ever as good as its fundamentally flawed model. Let's look at the pillars. Top left, nonlinearity. Real fluid dynamics, they don't scale in perfectly straight lines. Top right, structural coupling. Your variables physically interact with each other. Bottom left, modeling errors. The math is never, ever perfect. And bottom right, hardware execution. Physical parts have mass, and sometimes they just break. Keep these 4 enemies in mind for literally every design question you face. Which brings us to Section 4, hardware execution failures, and the sheer tyranny of physics.
So how does this play out in a real exam question? Well, professors love throwing temporal delays on tests. A perfectly coded algorithm running at the speed of light means absolutely nothing if you ignore the physical timeline of an action. Think about it. You send a control signal, but nothing happens instantly. First, you have dead time. That's the unavoidable transit delay while a fluid actually travels through a pipe to reach the sensor. Then you hit valve inertia. Physical valves are heavy, metal objects. They lag behind digital commands because they have literal mass. Only after all that waiting do you finally get a process reaction. If your exam model assumes instantaneous execution, your system is going to oscillate totally out of control.
All right, Section 5, the multivariable trap. Get ready, this is the final boss case study.
Okay, time for the heavy hitter, multivariable, or MIMO systems. Multiple inputs, multiple outputs. This is where everything we've learned collides. Here is our primary case study. And honestly, you'll probably see a variation of this exact diagram on your test. It's a coupled mixing tank. Our mission here is incredibly difficult. We have to simultaneously maintain both the physical fluid level and the fluid temperature, all while a totally random disturbance fluid pours in from the top. We've got a cold fluid input valve, a hot fluid input valve, a level controller, and a temperature controller.
Now, the absolute biggest rookie mistake, like guaranteed way to bomb the question, is falling for the illusion of isolated loops. It is so tempting to look at this and assume loop 1 acts all by itself. Oh, if the level drops, just open the cold fluid valve to fill it up. And then assuming loop 2 acts alone. If the temperature drops, just open the hot fluid valve to heat it up. I mean, it looks great on paper, right?
Just imagine a giant, flashing red warning sign right here. On the exam, you cannot treat a highly interconnected MIMO system like this as if it's just 2 separate, simple regulatory control problems happening in the same room. In physical reality, these variables absolutely do not exist in a vacuum. Instead, here is the fatal cross-coupling reality that you're going to have to explain on the test. Look at the cold surge. When the level control senses a drop in volume, it injects a surge of cold fluid to fix it. Makes sense. But that cold fluid acts as a massive thermal disturbance to the other loop. The tank's overall temperature suddenly plummets. So now, the temperature control loop panics and injects a massive surge of hot fluid to fix the heat, which overfills the tank and completely ruins the level balance all over again. One loop's cure is the other loop's poison.
Finally, Section 6, Mastering Complex System Control, the true art of engineering.
Look, to pass this exam, and honestly to actually make it as an engineer out in the real world, you have to anticipate and master this inevitable collision of variables. It's the true art of control engineering. Your ultimate objective when designing complex multivariable systems is to minimize that exact cross-coupling interaction effect we were just talking about. You have to build mathematical models that actually predict the physical collateral damage your controllers are going to cause. So, as you review your notes tonight, I want to leave you with this final crucial thought. Can you strategically pair your input and output variables to not just function cleanly in theory, but to actually survive physical reality? Think about it. Good luck studying, and I will see you in the next explainer.